I'm very happy today to introduce to have Martin Suderland speaking. Is here at NYU as a visiting postdoc, whatever that means, and he got his PhD with Evanthia and Lugano, and he's going to tell us about his recent work. Please go ahead.
Thank you for the introduction. Yes, and welcome to my talk on variant backwards analysis, which is applicable to order-dependent sets. I'm presenting you joint work with my PhD supervisor, Evanthia Papadopoulou. And yeah, the talk is a bit long, so if you have some questions, don't hesitate to also ask in between. Okay, so here's an overview of what I will talk about throughout the talk. First, I'll give you a presentation of the results. Then I'll introduce you a little bit to the standard backwards analysis. I've recently given a shorter version of this talk where I noticed that not so many people are familiar with it, so I'll give a small introduction there. Then I'll give you a small example where we can apply the backwards analysis. And then I'll tell you about how we can extend it to make it more general. And I'll give you two more examples how one can apply the more generalized version of it. The backwards analysis is a tool to bound the expected running time of randomized incremental algorithms. And usually, a requirement is that the output is order independent of the randomization order. But what we do in our variant is that we get rid of this requirement so that we can even analyze order-dependent outputs. We look at one example that Seidel has given. He has called this a bad example where standard backwards analysis is not applicable. And we show how with the new variant, we can actually analyze even that algorithm. And there we derive an n log n running time for this triangulation algorithm. So yeah, let's get into the backwards analysis.
Why is that a bad example?
So Seidel has given this example for showing that standard backwards analysis cannot be applied.
On this example?
On this example, yes.
Do you know why?
I'll come to that, yes.
Okay.
Okay, so what does standard backwards analysis do? It is a tool for analyzing the running time of randomized incremental algorithms. So here I'll introduce a little bit of notation here. So usually we work with n elements and we randomize these according to some permutation sigma. And I denote by Ti the running time of the algorithm in the ith step, and by Oi the output structure after that step. And the idea of backwards analysis is now that you analyze an algorithm as if it was running backwards in time from output to input. And that it's based on this observation that the cost of the last step of the algorithm can be expressed in as a function of the complexity of the output structure. So yeah, the let's say main bound there is that we bound the time complexity in the ith step for some permutation sigma by in terms of the output structure that we get after the ith step. And yeah, here I just write f for some function. Okay, so standard backwards analysis was introduced by Chu in 1985, where he used that technique to analyze a randomized incremental algorithm for the Voronoi diagram of points in convex position. And since then, many other applications were found, particularly Seidel. It was one of the people popularizing this approach. He gave many examples where backwards analysis can be applied, but he also pointed out one example, as I mentioned before, where it is not working. And yeah, the reason why in that example backwards analysis cannot be applied is that the algorithm's output has to be independent of the randomization order. I will,
You mean
Go
the
on.
final output?
yes, I will go more into detail later. So yeah, let's have a look at this example that Chu gave in his first paper about backwards analysis, constructing the Warner diagram of points in convex position. First, I define the Warner diagram of points. So we have endpoints in the plane. We call them sites. And then the Warner diagram is a subdivision of the plane into regions, where the region of a site consists of the set of points that are closer to that site than to any other site. So yeah, I've highlighted the one region of this region of the site as I. And yeah, the Warner diagram, the Euclidean Warner diagram of points is well studied. So even for any dimensions, the complexity, the worst case complexity is known, and also an efficient algorithm for computing it. We will only focus on the two-dimensional version, and note here that the diagram has linear complexity, and it can be computed in n log n time. Now, if the points are not in arbitrary general position, but if they have special position, like when they are in a convex position, then we can actually do better, and that is what Chu's algorithm is doing. So it takes advantage of, let's say, the simple structure, and that also we know the order of the points along the convex polygon. So yeah, I have an example of such a Warner diagram of points in convex position. We can see that it is a tree structure. There's also, as in the general case, it has linear complexity and all the regions are convex. So let's have a look at Chu's algorithm, how to compute this diagram. So as input, we take the vertices of a convex polygon, and it is important that we know these points in counterclockwise order. And the output is just the Warner diagram of these points. And the way how this algorithm works, it first picks a random permutation, and we insert the points one by one according to this permutation. And we keep updating the Warner diagram of the first many points. I have a visualization of how this algorithm works. So here I use the insertion order 264351. We have these 6 points in the beginning. We ignore all of them except for 2, and we construct the Warner diagram of these 2 points, which just is basically splitting the plane into two half planes by one line. Now it becomes more interesting once we add the next point, which is now P4. Since we know the cyclic order of the points, we know that P2 is the point before and P6 is the point after. So we therefore also can conclude that there's an unbounded bisector between P2 and P4 in the updated diagram. So we start with this bisector. We go from infinity, trace it towards the diagram until we hit an edge the first time. And then from there, we change the bisector, which we are currently looking at. Here we go from the bisector from between P2 and P4 to the bisector of P4 and P6. And we see that we leave to infinity. So we update the diagram by just adding this region of P4 and eliminating the edges that are covered by this region. Okay, then yeah, the next point that I insert is P3. Again, we are doing the same principle. We are tracing from infinity the boundary of this new region until we hit the currently computed diagram. Each time we hit an edge of the previously computed diagram, we change the bisector along which we trace, and like that we complete the region the currently added point. So we keep updating like that. So far, we have seen only small updating steps, but now in the last step, when we insert the last point P1, we see that we actually need a few more edges when we update the diagram. So here we actually have to add 4 more edges. Note that there can be instances where the updating step is quite cheap, but then in worst case, it can actually be that there is an edge for each point that is already in the diagram in the updating step, as almost in this case. So in general, this algorithm has a worst case complexity of n squared, but we will see that with the standard backwards analysis approach, we can show that the expected running time of this algorithm is actually only linear. Yeah. So let's have a look at the updating cost of the ith step. So if we denote by this m, the number of edges that we need to bound the new region, then the updating cost for the cost for tracing the boundary of this new region is actually linear in n. Yeah, when we actually do this tracing, we have to scan. Point that out. We have to scan this tree that is part of this updated region. So in here we see this tree of the old diagram. That one we have to scan, and that's basically the reason why we take linear time in M. So we already know that the diagram, if we only insert I many points, has O of I complexity, because then also each point is equally likely to be the last point. We can therefore conclude that also the complexity, the expected complexity of the last region that we inserted is constant. Yeah, so in total, if we take the complexity of all the regions, they have O of I complexity, but since they are O regions, each of them has to be expected of constant size. And as we have seen in the previous slide, the cost of the ith step depends linearly on the complexity of the ith region. So therefore, also the updating cost in the ith step is constant. Yeah, then from there we can directly conclude if each step takes only expected constant time, then in total, if we do that n many times, the algorithm will only take O of n time in expectation. And yeah, one key requirement that we used here implicitly is that the Brodner diagram is order independent of the insertion order as we added the points. So we made this argument that the expected complexity of the ith region that we inserted is constant. We can only make this argument if there's a collection of permutations for which we get the same output. So no matter which one was the last point that we inserted, we need that the diagram is independent of that. So now let's see how our variant of backwards analysis works, which tries to avoid, or which avoids this requirement of having order independent output. So what we want to do is we want to look at the groups of similar permutations, and each such group consists of permutations of length I, and they have one representative permutation, which I call sigma here. And the idea is now to bound the time that we need for processing an entire group by just the output structure of the permutation we get from sigma, the output structure that we derive from permutation sigma. So even though it can happen that I mean, the output structure of different permutations in that group are different, we only want to look at the output structure of permutation sigma. And then, yeah, similar to the backwards analysis, we have such a sequence of inequalities that we want to look at. So if we have
a group of similar permutations,
so
you're partitioning the symmetric group into groups of similar things.
yes, so I will go a bit into more detail later how we define them, but yes, we are partitioning the set of all permutations into groups of permutations where they have some similarities. And yeah, so now if we have any permutation in a group G sigma, then we want to bound the running time in the ith step for processing that permutation sigma prime by, that is kind of the standard, in terms of the output structure that we get from permutation sigma prime. But then now the special part of this variant is that we do this second inequality that we then in turn bound it in terms of the output structure of permutation sigma. Okay, so yeah, let's have a look now at these groups of similar permutations. If you're given a permutation sigma with the elements sigma 1 to sigma I, we define a shifted permutation where we just move the ith element of this permutation to the end. I call that permutation sigma alpha j. Okay, and then we define a group of permutations with representative sigma by including all these shifted permutations, where we once shifted each element to the end. Note that here we have this group contains the permutation sigma and all its shifted permutations, but still we only work with I many permutations because also sigma upper I is actually the permutation sigma. Okay. So now how TL already asked about this partitioning, how does that work? So we call a subset of the permutations Ri set of representatives if their corresponding groups partition the set of all permutations. So here I have an example for I equals 4. So we see here it includes 6 permutations. Each such permutation defines a group of permutations of size 4. So in total, if we would look at all the 6 groups, we get 24 permutations, and they would actually be equal to the set of all permutations of length 4.
What? So I equals 4. What is n? N is not anywhere.
Where's n?
There's no n.
Yes.
Well, Si, isn't it Sn?
Here I'm looking at Si. All the permutations of length I.
So R and I and n are the same.
There's no I. There's no n on this slide, right?
Okay. Does any? Okay. So only I. Okay.
Yes. So for problems independently of backwards analysis, it was already shown that such a group of such a set of representatives exists. Note also that such a set of representatives is not unique. So we just know about the existence, but that's also good enough. And yeah, then when we want to compute the expected time that we need for doing the ith step, we can do like the standard computation. We sum up all the over all the permutations of length I, compute the running time for processing these permutations, and divide that by the number of all permutations of length I. So that's the first formula here. And what we do now is that we can actually.
What's the size of Ri? You said Ri is not unique,
Yes,
but it can be of different it's going to determine Si.
yes. So these groups that we had on the previous slide, they have I many permutations in them. And one needs I minus 1 factorial many permutations in such a set of representatives.
And you say they are not, these Ri's are not unique, but are they basically variants of this example, or are they other examples?
I mean, of course, one can get variance by that, by just applying a permutation to
That's right,
this one.
but that's the only variant.
I'm not exactly sure, but it doesn't really matter. It's just that such a set of representatives has to exist for our application. We don't really care about how many there are.
So I have one question.
Yes, one more question.
There's a
Why is this
question.
lemma? What's there in this lemma? I mean, can't you just select Ri's greedily or something? What's there to, like, I could just select a permutation, look at G sigma, remove it from SI, and then continue.
He's asking whether you can just build it pretty greasily.
Yeah, no, you can't build it greedily. You basically have to make sure that you actually have a partition here. So if you would,
Okay.
if you
Sorry, I
greedy,
missed
you
that.
might
Yeah.
have an overlap in the groups, but you want that they are actually that there's no overlap of these groups.
Right, I missed that. Thanks.
Yes, but thank you for the question. Yes. Okay. Yeah, and then basically instead of summing up over all the permutations, we can actually sum up only over the set of representatives and compute the running time of such an entire group. So let's see how that works based on an example. Yeah, never mind. There's one more thing that I wanted to say here. So we want to then bound the running time that we need in the ith step for processing an entire group by the output structure that is just defined for the permutation sigma. So even though we have many permutations here in G sigma, we just want to bound it in terms of the output structure of permutation sigma.
So G of sigma, I'm just trying to understand the notation. G of sigma is what again?
G of sigma is this group of permutations, these I permutations.
I see. We
Consisting,
just
yeah.
move any I given position to the beginning.
You move it to the
iteratively,
end.
To the end. Not iteratively. Each time you apply to the original sigma.
Yes.
Okay.
Yeah. Okay. So maybe one is asking why would one choose exactly that kind of group? There are two reasons for that. So the first one is that we want to have that each element of the permutation appears exactly once as the last element, so that they have equal impact. And also we want to minimize the number of inversions between the base permutation and all the other permutations. And that is useful in order to have a similarity between the output that we derive from permutation sigma and the output that we derive from any other shifted permutation. So let's see how this can be applied for this triangulation algorithm. This is the algorithm that was pointed out by Seidel as this bad example, where the standard backwards analysis is not applicable. And yeah, let's see how this algorithm works. It takes as input a set of endpoints and a simplex in higher dimensions, but I will show all the pictures in 2D only. So we are working with a triangle here. And the output is a triangulation of the point set and this initial triangle. It works in a way that we incrementally add the points one by one, and we triangulate the area which contain the current point. So let's see how this works. In this case, in the example on the bottom, I'm showing you a triangulation for the insertion order 1, 2, 3, 4. So we process point P1 first. We check in which triangle it lies. There's only this one obvious now in the beginning, so we triangulate this triangle. Then we go to point P2, we look in which triangle it lies, and we triangulate that area too. And like that, we keep going through the points one by one. And we derive a triangulation of the entire thing. Let's see how we get the order dependency for this triangulation algorithm. So here I'm showing you triangulations for two different triangulation orders. On the left-hand side for the triangulation order 1, 2, 3, 4, and on the right-hand side for the triangulation order 2, 1, 4, 3. And we can go through the triangulation algorithm step by step now. Yeah, on the left-hand side, we triangulate with point P at 1 first, on the right-hand side with point P2. And then we keep going. And we already see here, even though we inserted the same set of points so far, we get different triangulations here. And then, yeah, we can keep going towards the end. And yeah, we just get different triangulations depending on the insertion order. So with our new variant of the backwards analysis, we can show that for any fixed dimension, this triangulation algorithm has O of n log n expected time complexity. And well, in order to achieve this, we need to maintain information while we are running this algorithm, which is mostly that for each triangle, we want to know the set of points that are lying in that triangle. And also the opposite, we want to know for each point, what is the triangle that it lies on. And yeah, when we want to maintain this information, we talk about rebucketing. One can think about it in that way, that each triangle kind of has a bucket of all the points that it contains. And yeah, then basically the running time of the entire algorithm depends on how many points we have to rebucket when we delete triangle and have to retriangulate that area. I have a little bit of a technical slide here. I will try to go over it a bit slowly. So I have three notations that I want to introduce. I have this partial triangulation Ti sigma, which is a triangulation that we get after processing I many points when we are working with permutation sigma. Then we have this term A Ji sigma, which is the union of triangles in that partial triangulation, which is incident to the jth point that we inserted according to permutation sigma. And then finally, we have this triangle notation, which specifies a triangle in a triangulation which only inserted I minus 1 many points. And there we are looking at this triangle that contains the last point. And one key observation that we have is this one here. Let me break this down a little bit for you. So on the right-hand side, we have this term that I defined before. So this A Ji sigma. It's this union of triangles that we get after inserting I many points to the triangulation, which is incident to this point P sigma j. And on the left-hand side, we are looking at the triangle that if we were inserting this point P sigma j last, this triangle which would contain this point. So on the bottom, I have an example. So yeah, on the right-hand side, we have the partial, or actually got the complete triangulation for the insertion order 2, 1, 4, 3. And we are looking here at the area that is consisting of all the triangles incident to point P1. If instead we are looking at the triangulation, which inserts point P1 last, which we get here, but we actually only insert 3 penny points, then this triangle that contains the point P1 is a subset of this area here. That's what the lemma says. So in summary, it gives us a relation between the output structure that we get from permutation, shifted permutation sigma j, and the output structure that we get from a permutation signal. From this technical lemma, we can conclude that in this triangulation algorithm, when we do the ith insertion step, each of the remaining points that need possibly rebucketing have to be rebucketed at most 3 many times when we consider an entire group of permutations. So if we then calculate the running time that we need for processing this triangulation algorithm, we can apply basically our standard formula. Here we are computing the running time that we need for all the n steps. So we sum up the running time that we need for the ith step. So that's the running time for the ith step. That's the formula also that we had seen before for the variant of the backwards analysis. And we can directly plug in our observation here that in the ith step, in processing an entire group, we have to rebucket the remaining points at most 3 many times. So that's what we plug in here. And if we simplify that, taking advantage that there are such a set of representatives has size of I minus 1 factorial, we can cancel that out in the numerator and denominator. It simplifies to this term, and we get the n log n running time. Okay. There is another example where one can apply this variant of backwards analysis, namely the Warner-like diagrams. These are interesting to perform site deletion. And let me introduce you to that first by looking at site deletion, where we consider points as sites. So on the left-hand side, we see a Warner diagram of points, as we have seen before. And when we want to delete the point S, we want to update the diagram. So what needs to be done there is we have to remove the region of site S and compute a tree in that region to replace the region. So on the right-hand side, we see the updated diagram if site S was not part of the Warner diagram, where the actual diagram consists also of these this red tree.
Right, that's the question.
Yes.
I have trouble seeing where the S on the picture is.
So site S is this point here.
All right, okay.
And we want to remove S from the set of sites.
Of course.
So we remove this region of S, and we need to see how to extend the remaining diagram within that region.
Okay.
So what we do is we remove this region and replace it with this red tree that we see here.
Okay.
Now for points, this is pretty simple, or actually Chu also showed that with this algorithm that we saw before for computing the Warner diagram of points in convex position, with some small modifications, one can apply the same algorithm, and this can lead to a linear time update algorithm. Now, points are pretty simple, and it gets much more complicated if we look at other sites. So here I have just compared, like on the left-hand side, we see the Warner diagram of points. On the right-hand side, we see the Warner diagram of line segments. Here there are a few properties that make it more complicated. On the one hand, one can see that the Warner diagram of line segments, the Warner regions of line segments don't need to be convex anymore. And moreover, two Warner regions can have can share more than one edge. So here we can see that, for example, this line segment, this black long line segment here, and this one, they share two edges in the Warner diagram. This one and that one. So these two properties make it more complicated when we want to do update after site deletion. So here I have a Warner diagram for line segment as sites. I didn't here in the diagram, we don't, in the picture, we don't see the line segments themselves, but the original Warner diagram consists of all the black edges, and this gray region is the Warner region of one line segment. When we delete that, we have to update the diagram in that region. And again, similar to the points case, we have to compute a tree there to do the update step. And yeah, Warner-like diagrams are a tool for doing this updating step for generalized sites. So they are an intermediate structure for doing such an incremental construction. Yeah, they work not only for line segments, but for abstract Warner diagrams, which is a bit of a bigger class. With these Warner-like diagrams, one can do this updating step also in linear time. It is very interesting that these intermediate Warner diagrams are order dependent, but the final output is not. So the final Warner-like diagram, when we insert, do all the insertion steps, corresponds to a real Warner diagram, which is again then order independent. Yeah, I have a summary of abstract Warner diagrams, but I don't think we have to get into detail there. But yeah, as I said before, abstract Warner diagrams are just a more general class. They cover the line segments as sites case, but they have some more cases as well where they are applicable. Okay, so as a summary, what we have done is we developed a new variant of backwards analysis, which is suitable for analyzing the expected running time of randomized incremental algorithms, where the output may be order dependent. We have shown that this new variant is applicable to this example that Seidel gave, where the standard backwards analysis was not applicable. And with this new technique, we can show this n log n running time in expectation. And yeah, we would actually like to find some more examples where this variant of backwards analysis is applicable. So yeah, we are looking for some randomized incremental algorithms where the output is order dependent, and then try to see if our new variant can be applied there. So if you have some ideas of
I thought your abstract said something about higher dimensional diagrams, something like that. That this technique will apply then. Did I read the abstract wrongly? I thought I saw something. High dimensional.
so for the abstract Warner diagrams,
No,
this
not
work is done
abstract,
for
abstract,
2D. But
your top abstract, I thought I saw something about high dimensional.
so this variant of backwards analysis can be used also for analyzing the running time of this triangulation algorithm in higher dimensions as well. So I've shown you all the pictures now in 2D, but
I see, that's what you mean.
the
by
same
high-
thing
I
applies
see.
for any fixed dimension.
But triangulation in high dimensional point, that seems a bit trickier, right? I mean, triangulations in high dimensions, even in 3D.
I mean, basically, you start with a simplex and a set of points in there, and then you incrementally add the points one by one. Each time you add a point, you look in which simplex it currently lies, and you partition that simplex by d+1 many simplices,
I see,
including that point as point.
I see, so it's not that difficult.
So the nice thing about this triangulation algorithm is actually that it is pretty simple, and yeah, that it serves kind of nicely as an example for a visual or for showing how this variant of backwards analysis works. Okay. Yeah, so that's it for my talk. Thank you for your attention.